Good afternoon, everyone. I hope you are all doing well. Welcome to today's 12th physics class. Okay. Before we dive in, let's talk about something we use every day. Yes, that is microwave oven. Yes. Have you ever wondered how it heats up your food so fast? Think about it. How the microwave oven heats up your food so fast. It's all thanks to something called dipole moment. Dipole moment in water molecule. Okay, in water molecules. Sorry. A water molecule, already you know the formula, water molecule. Yes, what is the chemical formula for uh, water? Is nothing but H2O. Yes, two hydrogen, one oxygen. Is it correct? Okay. So a water molecule H2O has a bent shape, not a straight line. Already you know that. Yeah. So like this, oxygen, one hydrogen, not a straight line shape. It has a bend shape. The oxygen atom is highly electronegative, meaning it pulls the shared electrons from the hydrogen atoms closer to itself. Okay. The oxygen atom is highly electronegative, meaning it pulls the shared electron from the hydrogen atom, which is closer to itself. Okay. So this makes the oxygen side of the molecule slightly negative and the hydrogen side slightly positive. Okay. Like that. You can imagine that. So here minus, here positive, positive side. Okay. Because there is a separation between these positive and negative centers of charge. The water molecule acts like a tiny electric dipole. Okay. There is a separation between these positive and negative centers of charge. So that's why water molecule acts like a tiny electric dipole. So when you put food in the microwave oven, the microwaves are a rapidly oscillating electric field that makes this water dipole spin and flip to align with this field. சரியா? Okay. So that microwaves are a rapidly oscillating electric field that makes these water dipoles spin and flip to align with the field. This constant rotation and friction generates heat that cooks your food. Okay, right. So our topic for today is the electric dipole on axial line and equatorial lines. Okay, we will learn what an electric dipole is, derive the formulas for electric field on its axial and equatorial lines, and solve some problem and see how this concept applies in a real world. Okay. Okay. To get us started and warm up our brains, I have to share a three question to recall some of our previous concept like electric field and Coulomb's law. Okay. I will share the screen. Okay. This is a first question. Oh, sorry. What? Why? Okay. Yes. Now it's okay. Okay. Good. So this is the first question. What is the formula for electric field due to point charge? If you know the answer, you can tell me via the chat box or unmute yourself. Yes, very good. Option 2. Okay, good. VOV2. Please change your name as your school name, please. Option 2. K into Q by R square. Okay. Option 2. ABRG. Okay. Okay. Super. Good. Any two? Good. RKSRG. Okay. Super. Good. Option 1. Yeah. Okay. Okay. Super. Okay. Good. Good. Okay. So, what is the formula for electric field due to point charge? We can choose option 2. Okay. Let me check. Okay. And second question. According to the Coulomb's law, the electrostatic force between two point charges is directly proportional to the according to the Coulomb's law, the electrostatic force between two point charges is directly proportional to the distance between the charge or square of the distance square of the product of the magnitude of the charge. Option 3. Okay. Option 3. Option 3. Okay. Good. 3, 3. Okay. Good. Okay. Good. So product of magnitude of charges. Okay. Then we will move into the last one. Third question. An electric dipole consists of. What do you mean by electric dipole? Already you are familiar with that term. Coulomb's law, point charges, electric dipole. Yeah. So electric dipole consists of two equal and opposite charges separated by the small distance. Okay. Electric dipole consists of a pair of equal and opposite charges separated by small distance. Yes, correct. Okay, good. Option 4. Yes. Option 4. Yes, correct. Very good. So let me check. Sorry. Okay. Okay, what is the formula for electric field due to point charge? Option 2, K into Q by R square. Very good. Great, great. According to the Coulomb's law, the electrostatic force between the two point charges is directly proportional to product of the magnitude of the charges. Okay. An electric dipole consists of a pair of equal and opposite charges separated by small distance. Okay. Great. Very good. Super. All right. Okay. So times after the quiz. I hope that was a good refresher. Now let's start with our main topic, axial line and equatorial line. Okay. First of all, again, I will redefine the electric dipole. Okay. So electric dipole is nothing but it is a simply a pair of equal and opposite charges. Say plus Q minus Q. But separated by the small distance. Separated by the small distance. So small distance denoted as 2a. So a means, so this is the origin. A means the distance between the center to one charges and same distance. Center to another charges. So total a plus a, 2a. So electric dipole is nothing but it is simply a pair of equal and opposite charges separated by small distance 2a. The key characteristics of the dipole is its dipole moment. Very, very important property of the dipole. That is dipole moment. So, which we denote with the letter small p with vector symbol. Okay. So, we denote with the letter p. It is known as a dipole moment. Dipole moment is a vector quantity. Already you know that. So, here vector symbol. So, it is a vector quantity. Okay. Its magnitude is given by the product of the magnitude of the any one of the charges and the distance between them. For example, P equal to magnitude of the dipole moment is equal to magnitude of the any one charge, because already we know that equal and opposite charges. So the values are same. So 5 coulomb, 5 coulomb, minus plus 5 coulomb, minus 5 coulomb, 6 coulomb, minus 6 coulomb. So magnitude of the charges same. So P is equal to Q into distance. Okay. Dipole moment is a vector quantity and its magnitude. This is a magnitude is given by the product of the magnitude of the one of the charges and the distance between them. So that's why P is equal to Q into 2A. Okay. So already we know that dipole moment is a vector quantity. So it has direction. Yeah, it has direction. So the direction of the dipole moment is always from the negative charge to positive charge. Please note it down. Very important point. Dipole moment direction always from the negative charge to positive charge. So from negative to positive charge. This is a dipole moment direction. Is it clear? Okay. Now let's visualize this axial line. Axial line is a line passing through the both charges. Q, Q plus Q minus Q distance, 2A distance. Okay. 2A distance. Okay. So the line passing through the both charges, it is known as axial line. It is known as axial line. So here black color line denotes the axial line. Okay. So in this axial line, we can put any one test charge like that. So for example, here, this is a test charge because we have to calculate the electric field of the charge at this point. So this is a point number, we can say any, for example, X or Y, something like that. Okay. So this is axial line. This is a point. In this point, we can put one charges in that position to find the electric field of these charges along the axial line. Okay. Okay. For equatorial line, plus Q minus Q and 2A distance. So equatorial line is the line passing through the center of the dipole and perpendicular to the axial line. Okay, here you can see that center of the dipole here. Yes, this is the center. So the line passing through that center of the line like that. And in that case, we can choose point this, for example, so X, and we can put test charge here. Okay, right. So from this position to this charge and from this position to this charge, always a same distance. That's why equatorial line. So for example, this is 5 centimeter. This is also 5 centimeter. This is 6 centimeter. This is also 6 centimeter. Okay. So this is a for equatorial line. Equatorial line is a line passing through the center of the dipole. Okay. And here plus q and minus q, the distance between the this point to this charge or this point to this charge always same. The magnitude of the electric field at C due to plus q and minus q are the same because C is equidistance, C or x. Okay, so x is equidistance from the plus q and minus q. Okay, right. Now I am going to derive the expression for the electric field intensity due to dipole on its axial line. We will use our knowledge of electric field from individual point charge and vector addition. We will find that for a point far away from the dipole, the electric field is inversely proportional to the cube of the distance. That means, okay. So what that here you can see that electric field is inversely proportional to the cube of the distance. Okay, right. E axial equal to 1 by 4 by epsilon naught 2 p r by r square minus a square whole square. For example, the electric field due to the point charge plus q to some other point in the axial line, E plus, we can take E plus, okay, because of due to positive q. So then formula here, okay, so we can say, see, this is plus q, this is minus q, 2a distance, okay, and r, we can put r is the distance between center of the dipole to this point, so this is r, and a means already you know that the distance between the one charge to center, a. So from this term, we can write E plus electric field at a point C due to plus Q is E plus equal to 1 by 4 by epsilon naught Q by R minus A the whole square. R minus, so sorry. So here minus Q, here plus Q. Okay. So R minus A, because we have to put the distance between the charge and the test point. So R minus A the whole square gives the distance between the plus Q to C. That's why I am putting this. Now again for the E plus charge, E minus charge. Okay. For that, E minus. So E minus electric field means electric field due to the minus Q charge from this point to this point. Okay. Okay. So now you can see the distance between this point to this point. A plus R. So E minus 1 by 4 by epsilon naught Q by R plus A the whole square. And you can put that vector symbol, that is P cap later. Okay. So this is a electric field due to point minus Q at C. So to find the total electric field, we have to add that E plus vector and E minus vector, and then we get 1 by 4 by epsilon naught 2 PR by R square minus A square the whole square. Okay, right. For a short dipole, for example, short dipole means R is double greater than A. So A means the distance between the center to any one charge. R means center to that point. Okay. So R is double greater than A means it denotes a short dipole. In that case, E axial approximately 1 by 4 by epsilon naught, because in this case R is double greater than A gives R square only. Yeah. So we can neglect the A term like this. Okay. So R square square R power 4. R power 4. So we can cancel R power 4. So we will get R power cube. So this is a electric field due to point charges along the axial line. Let's do the same for equatorial line. We will see that electric field direction is opposite to the dipole moment direction. Okay. So again, for the equatorial plane, equatorial line, minus Q plus Q. So this is C. This is origin, center, R. Okay, right. This is A, this is A. Plus Q minus Q to A distance. Okay. For the equatorial plane, we will get 1 by 4 by epsilon naught P by R square plus A square the whole power 3 by 2. This is a formula for, this is the equation for, or this is the expression for equatorial plane. 1 by 4 by epsilon naught P by R square plus A square whole power 3 by 2. Because electric field due to minus Q charge at point C and the electric field due to plus Q at C include theta. Yes, that's why it becomes like, for example, E total gives cos theta P cap minus E minus cos theta P cap. So this is a formula for to find the total electric field at point C. Okay. So sum of the parallel component of the E plus and E minus and its direction is along minus B direction, because already we know that dipole moment direction is always from negative to positive. Here, total electric field like that. Total electric field like that. Okay. Because this is for E plus vector. This is for E minus vector. So this is a E total vector. Then the direction minus P vector. Okay. So its direction is along minus P. This E total direction along the minus P direction. That's why we have to put minus P here. Then we will get like this. Okay. So as usual, E plus and E minus vector same because of due to equatorial line. Electric field due to this point at here, and electric field due to this point at due to this point this charge is same because of equatorial line. So E plus and E minus magnitude of that E plus and E minus are the same. 1 by 4 by epsilon naught Q by R square plus A square. Then we will get this expression. Okay. For a short dipole, R is double greater than A. So then E equatorial gives approximately 1 by 4 by epsilon naught P by, so R square and 3 by 2. We can neglect the A because of already you know that R double greater than A. So square cancel. So R power cube. So this is a expression for electric field due to equatorial line. Okay. 1 by 4 by epsilon naught P by R cube. Okay. And now let's use the simulation to see these concepts in action. I will share the screen once again. For equatorial plane and equatorial line. Okay. Right. So here you can see that plus Q charge and minus Q charge separated by the distance. So here these lines are imaginary lines, which is a electrified lines. And here you can see the minus, yellow color ball, yellow color point, okay, test point. So this is axial plane. We can choose the value of the charge, 5.3, 5.6. In that case, you can see that line changing because this line denotes the strength of the positive charge, strength of the field. Yeah, due to that point charge. So if we increase the value like that, you can see that denser line. If you decrease the value of the charge, we can see the less dense line. Yes. Okay. All right. So the electrified lines always start from the positive charge and end from the negative charge. That's why you can see that a green color arrow mark away from the positive and end at the negative charge. Okay. So now we can also separate the charge like this. 85, 75, like that. Okay. So for every value changing, you can note that down and calculate the electric field line at the yellow color point. Yes. So this is a axial line. So here you can see that magnitude of that electric field line 1.31 e power 1 Newton per Coulomb. Okay. Right. So observation point position 200 meters 0.0 centimeter, distance 200 centimeter. Okay. For the equatorial plane, now you can see that. So this is a equatorial plane. In that case, you can easily see that same distance. Sorry, once again. Yes. So equal distance from both charges. That's why equatorial plane. And you can draw the one line from the center of the dipole to that point, test point, and you can label it A or 2A. Okay. So here you can find that electric field. So here you can find the electric field due to positive charge and due to negative charge. So we have a formula E equatorial equal to 1 by 4 by epsilon naught P by R cube. P by R cube. Is it correct? P by R cube. But for axial line, 2P by R cube. For axial line, electric field 2P by R cube. For equatorial line, P by R cube. So you can see that there is a difference between the axial line, electric field, and equatorial line, electric field. This term, only two difference. So electric field of the axial line is twice the electric field line of the equatorial plane. Okay? Is it correct? Okay. So, okay. So, let's apply these formulas, equatorial line and axial line, by solving couple of problems. Problem number 1. Calculate the electric field at a point 0.1 meter along the axial line of a dipole with charges plus or minus 2 microcoulomb separated by 0.02 meter. This is a problem number 1. Calculate the electric field at a point 0.1 meter along the axial line of the dipole with the charges. Already I told you equal and opposite charges. So plus or minus 2 microcoulomb separated by the 0.02 meter. Okay. So first let's identify our variables. Here you can see that Q and distance A, 2A distance, and from that you can calculate the A, and here R. Yeah. So Q, 2 into magnitude of the charge, 2 microcoulomb. So micro means 10 power minus 6 coulomb. 2A, 0.02 meter. So which gives A is equal to 0.01 meter and R 0.1 meter. So now we have to find dipole moment P. Already I told you that is a formula for dipole moment Q into 2A. So just put those values 2 into 10 power 6 coulomb into 2A 0.02 meter. Then we will get 4 into 10 power minus 8 coulomb meter. Okay, like that. You can check it that. Okay. So this is a dipole moment. But we have to find the electric field on the axial line. So for the axial line or equatorial plane, we have We should have the value for dipole moment. That's why we will calculate first. Then we will move into the expression for the axial line and equatorial line. Okay, right. And here you can see that R 0.1 meter, but A 0.01 meter. Yeah. So R is double greater than A. R is double greater than A because 0.1 meter is very much greater than the 0.01 meter. Yes, correct. Okay. So then we will calculate for the short dipole. Yeah, because R double greater than A. So we can use the simplified formula for the short dipole. So V axial 1 by 4 by epsilon naught 2p by R cube. Right. So value for that 1 by 4 by epsilon naught 9 into 10 power 9. Already you know that from the Coulomb's law. And 2 into what is the p value? 4 into 10 power minus 8 divided by R. What is the R value? 0.1 cube. So then 9 into 10 power 9. 2 into 4, 8. 8 into 10 power minus 8. 0.1 the whole cube. So we can write 1 into 10 power minus 3. Yeah. 1 into 10 power minus 3. Okay. 9 into 8, 72. 72. And you can check that 10 power. Then we will get 10 power 4. Is it correct? Yeah. Because 10 power minus 3 goes up and it becomes as 10 power plus 3. And 10 power plus 3, 10 power 9, 10 power 12, 10 power 12, 10 power minus 8. So 10 power 4. So 72 into 10 power 4. Or we can write 7.2 into 10 power 5 Newton per Coulomb. This is a unit for the electric field, Newton per Coulomb. So this is a electric field on the axial line. 7.2 into 10 power 5. 10 power 5 or 72 into 10 power 4. Okay, right. Now, problem number 2. For the problem number 2, let's find the electric field. Electric field at a point 0.1 meter on the equatorial plane for the same problem number 1. Okay, of the same dipole. So same scenario in that problem number 1. So now we have to find electric field at a point 0.1 meter on the equatorial line of the same dipole. So we use the same dipole moment. Yeah, because charges values not changing. So same we can use the same dipole moment P. 4 into 10 power minus 8 Coulomb meter. And the same distance R is equal to 0.1 meter. Is it correct? 0.1 meter. So we use a simplified formula for equatorial line for a short dipole because already you know that R is double greater than A. So we can use the short dipole. Okay. So in that case, Okay. Okay. So just put that values 1 by, sorry, already we have the values 9 to the power 9 into, what is the value of P? 4 into 10 power minus 8 by, what is the value of R? 0.1 cube. Is it correct? Okay. So we can write 0.1 cube into 1 into 10 power minus 3. So like that. Okay. So 9 into 4, 36. And as well as 10 power 4. So 36 and into 10 power 4. So we can write 3.6 into 10 power 5 Newton per Coulomb. Newton per Coulomb. Okay. So this is a electric field on the equatorial line. Okay. 3.6 into 10 power 5 Newton per Coulomb. Please remember that electric field on the axial line is 7.2. Yeah. 7.2 into 10 power 4, 10 power 5 for axial line for the same dipole. Here, equatorial line. You can see the difference. Yeah, yes. 7.2 divided by 2, which gives 3.6, or 3.6 into 2, which gives 7.2. So, electric field in that equatorial plane is half of the electric field due to the same dipole, for the same dipole due to the axial line. Electric field is stronger on the axial line than on the equatorial line for the same distance. So electric field line, electric field is stronger on the axial line than on the equatorial line for the same distance. Okay. Now let's take a quick 5-question quiz to check your understanding of today's lesson. I will share the screen now. Okay. So this is a first question. The direction of the electric dipole moment vector P is from. The direction of the electric dipole moment vector P is from where to where? Yes, very good. Option 2, okay. Option A, okay. So P means already I told you dipole moment vector. So dipole moment vector has direction as well as values. So dipole moment vector P direction, yes. Option A, okay. Yeah. What is the exact or correct answer for the first question? Any option? Any other schools? The direction of the electric dipole moment vector is always from Yes, always from, yeah, good, super, good. Negative to positive charge. Okay, good. Second question. The electric field at a point on the axial line of a short electric dipole is directed. Electric field at a point on the axial line of a short electric dipole is directed opposite to the dipole moment vector, along the dipole moment vector, perpendicular to the dipole moment vector, or at a 45-degree angle to the dipole moment vector. So already I told you, axial line means there is a line which goes through the axis of the dipole. We can choose the one point or test point in the axial line. In that point, you can find the electric field due to the individual charges. So here you can see that net electric field due to because of net electric field, which is sum of the electric field of the individual charges. Yeah, but the electric field at a point in the axial line of the short electric dipole is directed E net always B to C. Okay, C. Okay, to C. Okay, okay, right. So I want to share one mm, information, that is E plus and E minus. Yeah, positive charge on one hand and negative charge in another hand. Okay. So which charge has more strength of the electric field? Which one? Positive or negative? Which one has stronger electric field? Positive charge or negative charge? Yes, positive charge. Yes. So, for example, if we can say plus 5 microcoulomb and minus 5 microcoulomb. So plus coulomb, plus 5 microcoulomb has stronger electric field. So always net electric field is along the dipole moment vector. Option 2, very good, great. Along the dipole moment vector. E net for the axial line, okay? E net along the dipole moment vector. So EP along the same direction. But in the case of equatorial line, for the third question, you can easily say that electric field at a point on the equatorial line of the short electric dipole means directed. Already I told in the class, E and P, 1, A, 1, 1. Yes, very good. Good. Yes, super. Option 3, C, C, 1. Okay, good. Yes. In that class, we saw that net electric field E in the direction of opposite to the dipole moment vector. That's why I am putting minus V vector. Yeah. So the electric field at a point, yes, one is correct. Electric field at a point on the equatorial line of a short electric dipole is directed opposite to the dipole moment vector. But in the axial plane, it is along the dipole moment vector. In that case of equatorial plane, it is opposite to the dipole moment vector. Yes, correct. Very good. Now, fourth one. For a given distance from the center of a short dipole, how does the magnet of the electric field and the axial line compare to the magnet of the equatorial? Very, very easy question. Yeah. Axial field is half the equatorial field. Axial field is equal to the equatorial field. Axial field is twice the equatorial field. Axial field is 4 times the equatorial field. Which one is correct? 1, 1, 1, 3. Okay. Which one is correct? Which one is correct? Axial field, electric field. 3, C, C. Yes, correct. Very good. Good. C, 3, 3, C. Yes. Yes. Very good. So already I told you for the equatorial plane, formula for the E net or E total 1 by 4 pi epsilon naught P vector by R cube. But in the case of axial field, it is 2P by R cube. So axial field is twice the equatorial field. Is it correct? Axial field is twice the equatorial field. Yes, very good, students. Very good. Super. Now, fourth one, very important question. How does the magnitude of the electric field on the axial line of the short dipole depend on the distance r from the center of the dipole? Please remember the formula. Yes, 3, 3, yes. C, C, okay, good. Please remember that formula for the electric field on the axial line of a short dipole. For the equatorial line or for the axial line, electric field is directly proportional to or inversely proportional to one quantity in terms of R. Okay. In this formula, in this expression, we can see that another one term, that is P. P means nothing but dipole moment. But electric field mainly depends upon the distance, that is R, from the center of the dipole. Yeah. So E is directly proportional to R. Yeah, yeah, very good, very good. C, C, C. Ah, yes, good. So E is directly proportional to 1 by R cube. Yeah, very good. So now we can check that answer. The direction of the electric dipole moment vector is P from, yes, always negative to positive charge. And for the second question, electric field at a point on the axial line of the short dipole is directed along the dipole moment vector. Okay. For the equatorial line, the opposite to the dipole moment vector. That's why we can put E total minus P direction. Yeah. Okay. For a given distance of center dipole, yes, axial field is twice the equatorial field. And the final one, yeah, yes, E is directly proportional to 1 by R cube. Clear? Very good. Very good. Super. Fantastic. Let's discuss. Can a couple of you volunteer to explain the key difference between the electric field formula for the axial and equatorial lines? What did you notice in our problem solving? You can unmute yourself or you can chat via the chat box. Can you see the any difference in the formula of electric field formula for the axial and equatorial lines? Which one difference? Yes. Okay. Okay. Right. Okay, students. Thank you. So the key difference is a factor of 2 and the direction of the electric field. For the axial line, it is along the dipole moment vector. For the equatorial line, it is on the opposite to the dipole moment vector. Okay, very good. Now, homework. Please see that uh, this is an electric dipole consists of 2 point charges plus 10 nanocoulomb, okay, and minus 10 nanocoulomb separated by the distance of 5 millimeter. Calculate the electric field intensity or electric field at a point on the axial line of the dipole 10 centimeter away from the center. And for the same electric dipole as in the problem number 1, calculate the electric field intensity or electric field. Okay, you have to know that same name, electric field or electric field intensity. So that's why I am putting electric field intensity here at a point on the equatorial line at a distance of 10 centimeter from the center of the dipole. Okay. Please note it down. If you have any doubt, please ask me. So today class is over. Jai Hind, Jai Bharat, Jai Vidyashakti. Thanks students. Thank you teachers.